is the difference between gasoline autocatalyst and diesel catalyst?
Well, obviously the fuel to begin with, right?
Correct.
Okay, so gasoline, burns and produces lower oxygen, I guess, to the tailpipe. Requires the catalytic converter to function differently, a three-way catalytic converter, than on a diesel oxidation catalyst. The autocat for gasoline has got platinum, palladium, and rhodium, the three elements, whereas the diesel doesn't have the rhodium, so it's just platinum and palladium. But there's more differences than just simply that chemistry.
Right.
We have the chemistry of the ceramic monolith itself.
The substrate?
The substrate. This piece here, this is a 2 brick from a gasoline engine.
It's like glass, huh?
It's like glass. It's ceramic. It's silica based. So sand, melted based. So that's what this is. Easy to melt in a furnace. This is very easy to melt, flux, recover the platinum, palladium, and rhodium out of auto catalyst. But diesel is a whole different animal in that it's silicon carbide is the substrate. Now, this is an industrial diesel oxidation catalyst. It does the same thing as this is for a stationary engine, like a power generating unit.
Right.
But it's the same substrate as found on mobile applications. So truck diesel oxidation catalyst is the same substrate. Silicon carbide. A silicon carbide melts at a higher temperature. It is very difficult to recover the precious metals from the silicon carbide in the furnace.
Now, why is that?
Well, silicon carbide is a material that's used in many different industries. They use it to create abrasive grinding wheels, cutoff wheels. It's very stable at high temperature. It's used to manufacture crucibles for melting of metal. So a pot furnace, maybe a gas-fired furnace, would have a silicon carbide crucible in there that would contain the molten metal. Maybe it's copper, silver, gold, high temperature melting, around 2,000 degrees Fahrenheit, up to about 2,500 degrees Fahrenheit. Those crucibles will withstand that temperature. The thing about the silicon carbide, though, is when it melts, it becomes more like tar, real thick and gooey, versus the ceramic from AutoCat gasoline.
It doesn't do that.
It doesn't do that. It melts very easily, and it's a very viscous slag or free-running slag. And when that's poured out into the mold, then you can collect your metal button at the bottom, and then you've got your slag fraction on top, and it's easy to separate the metal from the ceramic when the pour is cooled. Versus with the silicon carbide, and you get the tarry mess in the furnace, the tarry mess is going to hang metal. And there's going to be losses to the flux, to the slag of the platinum and the palladium.
Right.
And so the smelter can lose money.
Yeah, absolutely.
And that's
lost in the slag.
That's the main reason that the smelters don't want to see much silicon carbide mixed in with the AutoCat coming into their operations because of the losses they experience to the slag. And they don't have much of a choice at that point but to take the cooled slags, crush them, and rerun them in the furnace.
I was going to ask they have to run this multiple times.
Maybe they have to
in
run
the
it more than once, twice. to try to dilute down that silicon carbide to get it to finally become a viscous, free-flowing slag so that they can recover those precious metals. At a high temperature, it's supposed to separate the metal from the slag.
Is that like the free carbons that are here in the carbon?
That's another issue. Now,
let's talk about that.
Now, I was talking about diesel oxidation catalyst,
Yeah.
which has silicon carbide as a substrate. Well, let's talk about DPFs, diesel particulate filters, okay? Those are also made from silicon carbide,
Right.
right? This is interesting. See that line? You see this has been dip loaded with one metal, and this is the other metal on this side. I just thought I'd point that out. It's
No, that's good.
kinda
Good
interesting.
visual. Yeah.
But here's the thing. What's the purpose of a diesel particulate filter? It's different than from a diesel oxidation catalyst. A diesel oxidation catalyst is to clean the exhaust from, those bad actors that get into the air, okay?
Right.
What is the purpose of the DPF? The diesel particulate filter is a soot trap. It's designed to trap the soot from burning of diesel out of that internal combustion engine.
Right.
Okay?
All that carbon buildup.
All that
right?
carbon gets trapped within the veins inside, and it traps the soot. So now a diesel particulate filter has carbon in two places versus a diesel oxidation catalyst has carbon as in the substrate as silicon carbide.
That's
so
different.
now in the diesel particulate filter you have the carbon in the substrate, right? But then you also have it as free carbon in the soot trap as it filters. Now when this gets crushed and goes into the furnace, what happens to the carbon? Well, the carbon is going to burn, it's going to ignite.
Bringing up
It's
temperatures.
exothermic, so it's a burning reaction that's occurring in the furnace, and it's not something that can be controlled easily. So then we see furnace temperatures rise beyond safe operating parameters, and it could, and it has in the past, led to a catastrophic meltdown of the actual furnace itself. The furnaces are generally, they have water cooling jackets around it to keep the shell of the furnace integrity cool enough so that the furnace doesn't cause problem.
Right.
But when this, free carbon catches fire,
It's a different story.
it's a different story. It runs up in temperature. They can't cool it down. It's going to do what it's going to do because they don't know how much carbon is it. So they have to control the amount of carbon that goes in. So there's those two reasons that the smelters, they want to keep these diesel products out of the pyrometallurgical process.
That makes sense.
Yeah, they want to keep it out. So really, what are your options at this point? Well, I guess you have a couple of options, right? First one is maybe you could crush this material and pre-burn it before it gets to the smelting operation. Well, that means that it's going to require more consumption of fossil fuel, more BTUs
Right.
to burn the carbon off, so a pre-burning operation. And then once it's burned, then it could be reintroduced into the furnace, maybe diluted with
Seems
other materials.
double handling.
Just double handling, double furnacing,
Right.
double. The cost is what's that, double?
Yeah.
And it's very inefficient, and it's something that is being done. I know there are some operations that currently do this. Limited capacity. They don't like taking it in. They don't like running the process.
Right.
They do it, but it's lower grade material. AutoCAD's high
they'd rather
grade.
Run this, yeah.
They have limited capacity, these smelters. They would rather devote that limited capacity to high grade AutoCAD
Right.
because that's where they make their money.
Right.
If you're running $200 a pound, $150 a pound AutoCAD
And
versus
more some of those.
versus you're running $30 a pound,
Yeah, it's a no-brainer.
and it's
Economics,
squeezing out capacity by using the low grade, squeezing out the high grade where they make their money. What do you think they're going to do? They're going to choose to say, we don't want to run the diesel
Right.
because we have limited capacity. So stockpile your diesel for a while,
Right.
fellas.
Till something new comes along into
So
the
something new
marketplace,
comes
right?
along, right? And then now, we have other issues that the pyrometallurgical process can't handle. One is, say, a foil converter. This is a foil converter here.
Rolled steel,
Rolled steel
Yep.
internally, right? And this has wash coat that's hosted on the surface of the rolled steel. This has to be mechanically shredded,
Right.
air separated to recover the powder. The powder has the precious metal. That can be introduced into the furnace. But you can't take this monolith from a rolled steel converter and go straight into the furnace with it. You've got to pre-shred, air separate, collect the powder.
Right.
I got a bag of powder in the lab I should have stuck on the table from this process, right? Would have been interesting to see. But it basically is very high grade. It's very similar to AutoCat in its consistency, and it's good feedstock for a pyro operation. However, the honeycomb itself is not.
Correct.
Okay. Now, if you get into the other industrial, this would be, we call it oxy brick.
Internally, we call it
This
oxidation.
oxidation catalyst from a stationary power generation. Picture a 5 by 8 foot
Engine?
block of these stacked together, right? That the exhaust blows through, maybe from a 32 cylinder engine that's generating electricity. Could be burning methane, could be burning natural gas, could be
Diesel.
burning diesel. But typically this substrate here, and we talk about the diesel. The diesel doesn't have any rhodium in it.
No, that's why it's a lower recycled.
It has a lower value because it has no rhodium.
Right.
It's a very high value. AutoCAD has rhodium.
Yeah. All three. Right.
And this industrial does not. Now, they make this as foil as well. This is a ceramic brick. I don't know if this is easy to see or not, but this ceramic brick, it blows through, it's easy to crush, hard to furnace. Why is this hard to furnace? Well, because most of the ones that we've come across are a substrate that's called aluminum titanate, and it doesn't melt.
No, that's going to
Easily.
be an issue forthcoming, right?
If it's a very low percentage mixed in with AutoCAD, maybe 1%, 2%, it'll furnace.
Yeah.
But if you're going to ship in 100% of this to the furnace operation, they're going to reject it. They're not going to take it in.
Right.
And so
Does it do the same tar effect or honey
Well,
effect when it's in the furnace?
this doesn't melt at all.
Oh, it doesn't melt at all.
This doesn't
Wow.
melt at all. So, whatever's in here. Sorry for the dust.
There's something in there.
Whatever precious metal is in here is going to be trapped
Right.
in the slag.
Oh, so then it's lost to the
So
slag.
it's lost to the slag.
Right.
So they don't recover the metal out of the slag necessarily. So what do you do with it? What can be done with it? Well, like I said, it could be diluted down into the feedstock of 99% of
With the auto
silica-based material, right? Or it has to go wet chemistry, right? And so wet chemistry is a great option for this because it doesn't require the melting of any of this.
Right.
And it's strictly, crush it, mill it, goes into the reactor. It's extracted wet and recovered after filtration. So the solids are filtered away. The liquors, the pregnant liquors, the precious metals are dropped out of solution, and that goes into the final separations for platinum, palladium, and or platinum, palladium recovery.
Right. Depending on the material.
Depending on the material. And so we have a great avenue for this. It's new technology on the market. It's finished its phase 1 trials. We're going into phase 2 pilot now, and production plant will be built by the third quarter of 23. So we're accepting 1-ton lots now, and
It's good to get their data points.
great recoveries. 99% recoveries on the wet chemistry side. And the thing is, the real difference is this. When you send to a smelter, they're not going to report and pay out based on production. They're going to report and pay out based on sampling the crushed stream. 3, maybe 5% of the material is taken off the crushed stream and gone to the lab for analysis, calculation back to the original 100% and paid out.
Right.
Versus with the wet chemistry, the entire lot is processed through to recovery.
So that's 100%.
It's 100%. So it's not
Wow.
it's not assay sample based.
No, it's
It's recovery based of the precious metals that are 99% recovered from this material. These are what the smelters would call deleterious elements, and they penalize on it. If your carbon is too high, they're going to kick it out.
Yeah, there's no carbon limit with the wet chemistry.
There's no
correct?
carbon limits with the wet chemistry. There's no aluminum titanate limits with the wet chemistry. There's no silicon carbide limits with the wet chemistry that we offer.
Right.
And it's a great solution.
It's a game changer.
It's a game changer. So we're really super excited about this offering. The end of 2022, we came to market with it. Early 23, real solid, volumes are going through the facility, moving on into a full-scale production plant. It's just good stuff. It's really good stuff. So, I'm excited about it. We're seeing great results. We have some suppliers that are in the program right now that are also just as excited as we are.
Absolutely.
Yeah, and it really kind of opens up. I mean, this type of material right here, this oxidation catalyst, has been a bane to the recycling industry for a long time.
Oh yeah, with what you just enlightened us all
Right.
with the furnace issues.
So it really has opened up a new pillar of revenue for some recyclers out there.
Yeah, absolutely.
Because I know that there's scrap metal recycling companies in the industry that see this on a regular basis,
Right.
and it goes to landfill.
Right.
And they lose the platinum and palladium value because they can't find a market. There has not been a market that existed until now.
Right.
So this is really super exciting.
It's been, sitting on the shelves, stockpiling somewhere out there in North America.
Well,
and
even
Europe.
with diesel particulate filters, DPFs, and diesel oxidation catalyst, there's warehouses full of this stuff in this country.
Mm-hmm.
Some of the larger auto recycling yards have stockpiled this material because it needed to be kept out of the stream going
Right.
into the smelter.
Right.
Now we could ship in 100% DPF material, 100% diesel oxidation catalyst material.
Right. Or even aftermarkets, keep it separated from your ultra, your high grade auto catalyst. Get data points on that
I know
too,
some
right?
companies would take in 100% and then they would mill it and they would pay out on assay in their terms. But then they have to dilute it back into the auto cat to get it processed.
Right. But
So,
this process,
so that's
you don't
reflected in their pricing.
have to. Right. And one other thing, this is a green technology and it's not acid based.
It's not acid
Not
based,
acid.
it's solvent based.
Mm-hmm.
So it's low energy, it's very small amount of off gassing, doesn't produce hazardous waste. The carbon footprint is minimal
Right.
in this process versus going to a traditional smelter.
Yeah. And it
Now,
can be,
I'm not knocking smelters. I mean, we need them
absolutely.
because, from what I'm seeing, the amount of platinum and palladium and rhodium worldwide that is being recovered from our industry right now is about 4.5 million ounces a year.
Currently.
It's going to double in the next 25 years because the loadings are going to get so much higher.
Right. The quantity of converters out there is going to be less.
Right.
But the quality is going to go up, like what you just said. Because
the
FDA standards,
the
right?
smelter capacities need to increase, right, to handle the volume of materials that are coming in the next 20, 25 years, okay, from catalyst. That's number one. Number two, they need to increase beyond the ounces that they have to recover because they have to wash their slags. They have to re-melt their slags. to get from their 98% recovery up to their 99% recovery.
Right.
They have to continually wash slags to do that, which is more energy,
It's tough.
more carbon footprint, all of that. So
Right.
that's why this wet chemistry is such a game changer and so exciting. And anyone that has any interest in, saving the environment and going green should seriously, especially as an organization, as
Right.
a company,
Right.
should really be looking at it, because this is something that you can put as a feather in your cap to say, we're going this direction with this material. Why? Because as an organization, we're doing this because this is our part.
Right.
We're doing our part.